In this video, we'll explain how to use automated guided vehicles, or AGVs as we call them in plant simulation. In the Mobile Units tab, you'll find the transporter. The transporter represents AGVs. AGVs can function as transporters, moving freely or following a designated track. In the first example, we'll employ a track for the AGV to shuttle parts between stations. Consequently, we've already positioned 2 stations. Now we will insert a track. Next, we insert a source and establish a connection with the track. Now we need to create a transporter. We can define the object which is created by the source by dragging it onto it. So we drag the transporter onto the source, configuring it to output transporters. In this specific scenario, only one transporter is required. To achieve this, we open the source dialog and set the amount to 1. To ensure the transporter moves in a circular path, we need to connect the end of the track with the start of it. After this configuration, we can start the simulation. Upon doing so, we will observe the transporter following the circular track. However, now we need to stop the transporter at the stations to load and unload the parts. To accomplish this, we insert a sensor at the first station's level. In the ensuing dialog, we create a new control. Within the control, our aim is to instruct the transporter to come to a halt. For better readability, we create a variable named AGV. Then we assign the anonymous identifier @ to this variable. @ will correspond to the caller of the method, which is the AGV. In the subsequent line, we can utilize the stopped attribute to bring the transporter to a stop, setting the variable value to true. Then we move the content of the station to the AGV. In the last line, we set the stop attribute of the AGV to false. We save our changes and place a second sensor at the level of the second station. Now we again create a control. Here, we once again aim to access the AGV. Therefore, we create a variable named AGV and assign the anonymous identifier @ to it. Then we set the stop attribute of the AGV to true. Now we can move the content to the station. Afterwards, we set the stopped attribute to false. Then we can save our changes. The sensors are currently named as on-sensor, which is not an appropriate designation. To rectify this, we open the track dialog and navigate to the User-Defined tab. From there, we select the respective sensor, click on Edit, and proceed to rename them accordingly. Once the renaming is complete, it's necessary to update the sensor's path. This can be accomplished by navigating to the Controls tab and selecting Sensors. From there, we double-click on the specific sensor and make the necessary adjustments. Afterwards, we can run the simulation. As we can observe, the simulation runs smoothly. However, it's important to note that at this stage, our code is not flawless. It is important to consider potential edge cases, such as the situation where the station's part is not ready upon the AGV's arrival. This scenario may occur if the station is still processing the part when the AGV reaches it. To address this edge case, we revisit the control. Here, it becomes crucial to initially assess whether the station is empty or not. Since we desire the AGV to wait until the conditions are met, we begin by incorporating a wait until statement. To determine if the station is empty, we can check if the station's content is unequal to void. To ascertain whether the part on the station is ready to exit, we need to identify a relevant attribute. To find a suitable attribute, we access the F8 dialog of the part. As discussed in previous videos, not everyone is expected to be familiar with all object attributes, and even experienced users adopt a similar approach. To pinpoint an attribute suitable for the wait until statement, it must be watchable. Let's start by filtering the entries for observable attributes. Now we discover an attribute named finished, which seems appropriate for our purpose. We select it and press F1 to consult the help for additional details. Here, we click on the first entry as it aligns with our search. Upon reading the description, we realize that it is perfectly suitable for our needs. Returning to the control, we now check if the part is finished. This is essentially the approach to finding suitable attributes for coding. Only if these conditions are met, we move the content of the station to the AGV. Now we save our changes. Then we set the processing time of the first station to 20 seconds and let the simulation run again. As observed, the AGV waits until the conditions are fulfilled. Now, let's address potential edge cases on the second sensor. Initially, we don't want to stop the AGV in case it's empty. Therefore, we introduce an if statement. In the condition, we aim to confirm whether the AGV is not empty. If this is the case, we stop the AGV. Then we move the content of the AGV to the station and set the stop attribute to false. Now, let's save our modifications. The second potential issue could arise if the second station hasn't finished processing the part. In this scenario, the AGV might proceed without waiting for the station to be ready for the next part. This can be illustrated by extending the processing time to 50 seconds and restarting the simulation. As observed, the AGV continues moving and delivers the part to the station in the next round. To address this issue, we can use a wait until statement and wait until the station is ready. If wished, we can incorporate a delay in the unloading of the part by utilizing the wait statement and waiting for 5 seconds. If we restart the simulation now, you will observe that the AGV waits until the station is ready to handle the next part. Next, let's take a closer look at the attributes of the transporter. To do this, double-click on the transporter to open its dialog. In the first tab, we find attributes related to the transporter. On the left side, we can adjust the size of the transporter, while on the right side, we can modify the booking point. This is analogous to the booking points of MU that we explained in previous videos. Additionally, we can set the speed of the transporter and specify if it should move backward. This is particularly useful if there's a track where the transporter can't turn and needs to move in reverse. As you may have observed, the transporter currently stops and starts very abruptly. To address this, we can check the acceleration checkbox and enter values for acceleration and deceleration to achieve a smoother appearance. However, it's important to note that if we set acceleration and deceleration, in this specific example, the AGV would only accelerate smoothly but wouldn't decelerate smoothly. This behavior is due to using the stopped attribute to halt the AGV, causing an immediate stop as soon as the relevant line of code is reached. In the second example, we'll demonstrate an alternative method to stop the AGV smoothly. Furthermore, in the tractor section, we can designate the transporter as a tractor. This option assigns the transporter as a tractor to a tugger train, which pulls or pushes trailers. Then we can specify a start delay duration. This is the time after which a transporter, which collided with the one driving in front of it, starts moving after the transporter driving in front started moving again. In the Load Bay tab, we can configure how parts should be loaded onto the transporter. The tab routing will be explained in the following video. The tab's failures and controls are equivalent to other objects' failures and controls. In the Battery tab, we have the option to configure whether we want to simulate the loading and unloading of the battery. We will now look at a second example. Here we can see 4 stations, 2 sources, and a track. The source connected to the track produces one transporter. The second source produces parts. In this example, we'd like to demonstrate an alternative method to move and stop the AGV, distinct from using the stopped attribute. Since we know the exact position of the sensors, we create them over the dialog of the track. Then, we navigate to the Controls tab and click on Sensors. Here we now add 5 sensors, the first one at 2 meters at the level of the source. The second one at 6 meters at the level of the first station. We repeat this process for each station. Upon completion, we now insert a method object into the frame and name it Transport Parts. Then we create an exit control for the source. In this exit control, we now invoke the method transport part and pass the anonymous identifier at as a parameter. As the source produces transporters, at will correspond to the AGV. After making these changes, we save our modifications and switch to the method. Here we now assign AGV as the name of the parameter of the method call. If you are not familiar with this, please refer to the video on Advanced SimTalk. Now, our objective is to make the AGV move to the level of the source, which corresponds to the position of the first sensor. To facilitate the AGV's movement, this time we utilize the method targetPosition. Thus, we aim to assign the position of the sensor. To proceed, we can open the dialog of the sensor. Next, we click on the question mark in the title bar and then on position. Here, the SimTalk attribute is presented to us. We can now incorporate this attribute into our code. In the next line, we can now use the wait until statement to wait until the target position is reached. However, keep in mind that we need to wait until the target position is equal to -1. The reason can be examined in the help. So we click on the method and press F1. In the help, we now scroll a bit down. Here we can see that the target position will be set to -1 upon reaching it. We now switch back to the method again. Now we can move the part from the source to the transporter. Now, our aim is to transport the part to one of the stations randomly. To accomplish this, we begin by storing each position of the sensors in an array. Arrays are employed to store multiple values in a single variable, eliminating the need to declare separate variables for each value. We create an array named positions to achieve this. Then, we use square brackets and add the positions of the remaining sensors, separating them by commas. In this manner, we have created an array of size with the corresponding positions of the sensors. We opt to use the sensors and the position attribute of the sensors for two main reasons. Firstly, the visual representation of the sensors allows us to easily decide whether they align with the stations and facilitates movement along the track, using the arrow keys in case of station adjustments. Secondly, adjusting the sensor position does not necessitate code modifications, streamlining the overall process. Now, we can add a print statement to display this array. After saving our changes, we can show the console and run the simulation. As you can see, the positions of the sensors are printed. Then we hide the console and remove the print statement. The values of an array can be accessed by referring to an index number. Since the array has a size of 4, we can access individual values using an index from 1 to 4. Therefore, we need to generate a random integer number between 1 and 4. This can be achieved using the uniform distribution. To implement this, we create a variable named random number, and we explicitly declare its type as an integer. This ensures that we obtain integer numbers between 1 and 4, rather than real numbers. We then use the uniform distribution, passing 1 and 4.99 as parameters. The upper boundary needs to be set to 4.99 to assure that each integer number is generated with the same probability. Now, we can set the new target position of the AGV and assign it to a random index of the array. Then we can simply use the same wait until statement from above. Now we need to move the part to the corresponding station. To do so, we create a new array which we call stations. In this array, we can store the stations. Then we can move the content of the AGV to a random index of the station. In this way, we will move the content of the AGV to the station at which it has been moved. If we leave the code as it is now, it would terminate after one execution. At this stage, we can make the method run endlessly by using a while statement. The while statement will be executed as long as the condition is met. To run the simulation infinitely, we can use true as the condition, which always will be evaluated to true. However, it's important to note that in this scenario, the simulation will never terminate. Let's save our changes and run the simulation. We again see that the AGV abruptly stops and starts. We can mitigate this by activating acceleration and restarting the simulation. Now, you will observe that the AGV accelerates and decelerates smoothly. In the last part of the video, we want to show AGVs in combination with the pick and place robot. To do so, we create a new model frame. We want to model that a pick and place robot picks parts from a station and loads them onto an AGV. To achieve this, we place a source, a station, and a pick and place robot. Afterwards, we insert a source and a track. Then we drag and drop a transporter onto the source and set the amount of produced transporters to 1. We can now easily drag the robot and drop it onto the track. Then we can select Load Part. By doing so, we instruct the robot to load the part onto the AGV. If we now start the simulation, we will see that the AGV stops at the sensor and the robot loads the part onto it until it reaches its capacity. This approach allows for the straightforward establishment of a production line by combining the pick-and-place robot with the AGV. To elucidate the logic behind this setup, we access the robot's dialog and navigate to the Exit tab. Here, we can observe the actions taken when we place the robot on the track. The target selection is automatically configured to load part onto MUX sensor. Following this, the target object is set to the track, and the target sensor ID is adjusted to correspond to the sensor on the track. With these settings, the robot will pause each AGV as it approaches the sensor, load parts onto it until capacity is reached, and then allow it to resume its movement. This concludes our video on an introduction to AGVs.